Hi folks, welcome back. We're talking today about section 2.7. The title of this section is Related Rates. And I do like to spend a little bit of time just dissecting the title of a lesson to make sure we pull out as much context as we can from that. So let's talk about the word rate. In this course, 9 times out of 10, when we're talking about a rate, it's referencing a derivative with respect to time. Okay, so if we have some equation that is a quantity, I'll just call it Q as a function of time, then the derivative of Q with respect to time will look like that, and that'll be the rate of change of Q with respect to time. So that's half of the title. The other half is related. So what we're going to be doing is looking at how different rates relate to each other within an equation. And that is the nuts and bolts of this section. And I'm going to start this off with a video example. So what I have here is a picture of a vase. Imagine that, it's a vase. And we're going to look at a video of this vase and some water pouring into it. And as you watch this video, I want you to consider the following two questions. The first question is the fill rate constant for t greater than or equal to 0? And t greater than or equal to 0 will be the point in time when the water is turned on. And the question 2 is the rate of change of the water height a constant? So again, read that very carefully. Is the rate of change of the water height a constant? If so, what is it? If not, why? And as I show you this video, well, let's see if we can get ready here to show it. Yeah, this is a vase sitting in my kitchen sink or near my kitchen sink. There are two different pieces of masking tape marked on the vase. And just for the sake of comparison, I think it's 1 inch wide masking tape, maybe 1.5 inches. That doesn't really matter. Let's just say it's 1 inch wide masking tape. And I'm going to go ahead and play this video and I will turn the water on. And as the water is turned on, I'm going to give you a couple different points in time where I say start and stop. And what I want you to do during those times is look at the time counter here on the bottom of the screen. So kind of measure the time it takes to fill for the length of, or the height of this piece of tape, and then we're going to do it again for this piece of tape. So without further ado, here's my awesome production quality home video of a vase filling.
Vase filling, take 1. Start. Stop. Start. Stop.
Well, that was thrilling, folks. Yeah, that's the vase filling in my kitchen sink. So now let's go back and address these questions. Is the fill rate a constant for t greater than 0? I think the answer to that question is yes. If you noticed, I turned the water on and then didn't change the setting for the faucet valve after I turned it on. So I turned it on and boom, we're going to assume that was a constant from that point forward. Second thing to talk about is the rate of change of the water height and whether or not that's a constant. Well, if we look at the way this problem was set up, there were 2 different heights we looked at. We'll just call this h sub 1. And then we had another one in here we'll call h sub 2. And if you were paying close attention to that time meter at the bottom of the screen, I think that the change in time for this first height was about 5 seconds. So if we can think about the rate of change of the water height at that time, we're going to take an average rate of change over the entire 1 inch wide piece of tape. And that'll give us something like this. dH dt, the rate of change of the height, there was about equal to 1 inch divided by 5 seconds, which is 0.2 seconds, inches per second. Beg your pardon. Oh no, don't turn me into the unit police. So that's 0.2 inches per second. Okay, now let's look at what happens at the second position, H2. For that one, I got a delta T of about 10 seconds. So that's going to give us, again, we're going to use the average rate of change of height there as our proxy for the total, for the instantaneous rate of change at these two different positions. So that's, again, the tape was the same width, so that's 1 inch, but this time it was 10 seconds. So that gives me 0.1 inches per second. And this is a classic related rates problem. The rate of change of the water volume was a constant, but the rate of change of the water height clearly was not a constant. We have two different rates here, and from the geometry of the problem, it should be obvious to you why this is true. The bottom of the vase is narrower, so for every second that the water's on at the bottom of the vase, the height's going to change more than when when you go up higher on the vase where it's wider. Okay, the wider the vase, the more volume it holds for each incremental cross section. So that is that is a basic related rates type problem, and we're going to now formalize our study of related rates. In this section, we'll be taking derivatives with respect to time. If you think about it, you might be able to figure that out from the title. After all, we are talking about rates. And I have some famous formulas here, and what I'd like you to do is take the derivative of each with respect to time. I'm going to go ahead and just rip through all of this stuff, and then I'll pause it at the end and give you some commentary about why I did things the way I did. Before I go ahead and rip through these, I do want to make a couple quick comments, and this is just to kind of build on what we've done in previous sections. If you remember in section 2.4, we discussed the chain rule. And the chain rule is how we take the derivative of a composite function. And then in section 2.5, we talked about implicit differentiation. Well, now in 2.7, we're talking about related rates. Related rates is an application of implicit differentiation. And then you hopefully remember from our discussion on implicit differentiation that it is an application of the chain rule. So we're going from chain rule to imp diff, and then imp diff to related rates. Okay, now I'm going to go ahead and rip through these derivatives with respect to time. Okay, so this first one says the rate of change of S with respect to T is equal to this whole expression right here. And I hope that you can just look at this formula and figure out I shouldn't have to ask this, but I will. What does this formula S equals the square root of x squared plus y squared represent? Well, that's the Pythagorean theorem. Okay, so that's an application of Pythagorean theorem. Might become important when we're looking at some rates of change of points with respect to each other. Now let's go over here and look at a trigonometric equation. I got tangent of theta equals y over x. That's one that shows up in our general study of right triangle trig. So I'm going to go ahead and differentiate that with respect to time. Okay, we'll do a quick pause on this one, just talk about it before I do any more algebra here. I'm taking the derivative with respect to time. So the derivative of the left-hand side, the derivative of tan theta is secant squared theta times d theta dt. Remember again, that's the chain rule in action there. The derivative of tangent is secant squared. The derivative of theta with respect to time is d theta dt. The right-hand side, I hope you recognize that I use the quotient rule there, low d high minus high d low divided by low squared. What I'm going to do now is I'm going to solve for d theta dt because that would be the rate of change of the angle theta with respect to time, and that might come in handy later. Okay, there's that one, folks. We got the rate of change of theta with respect to time. Oh, I do not like the way that worked out. The rate of change of theta with respect to time is x times dy dt minus y times dx dt, all divided by secant squared theta times x squared. Okay, let's now look at another example, this one for area. I hope you recognize 1/2 base times height as the area of a triangle. If I need to tell you that, you're probably signed up for the wrong class. Okay, so this one, this formula is a product. So the rate of change of area with respect to time, I'm going to need to use the product rule there. I'm going to factor out the 1/2 because it's a constant multiplier at the start. And then I'm going to say it's b times h prime plus h times b prime. And b prime and h prime there just represent the rate of change of b and h respectively with respect to time. Let's now look at the area formula here. This is pi r squared. I hope you recognize that as the formula for the area of a circle. And the rate of change of area there. Well, I have pi, which is a constant, times radius squared. Radius is the variable quantity there. So this one is going to be, let's see, it's going to be pi times, I have to differentiate r squared, so that's going to be 2r times dr dt. And I'm going to rewrite this as 2 pi r times dr dt. And I think this one's kind of interesting. You might hopefully recognize this. So 2 pi r is, that quantity is the circumference of a circle. So if I want to know the rate of change of area of a circle with respect to time, I multiply its circumference at an instant times the rate of change of the radius. So that's kind of a fascinating little fact for you there, where how calculus and geometry work together. All right, let's now look at some volume formulas. This one here is the volume of, this first one's the volume of a cylinder, pi r squared h. And the reason I'm doing these formulas, folks, is really just to give you practice of implicitly differentiating with respect to time with some formulas you've seen before. Okay, so this one, pi is a constant, so I'm going to factor that out right at the beginning. And then I have first times derivative of the second, because it's a product, I need the product rule. It's going to be r squared times dh dt plus h times the derivative of r squared. So that's going to be h times 2r dr dt. Okay, there you have it for that one. That's the rate of change of the volume of a cylinder with respect to time in terms of the rate of change of its height and the rate of change of its radius. The last formula we have here, this one, 4/3 pi r cubed, that's a sphere. And we only have one variable in it, so that'll be a little bit easier derivative than the previous one. It's 4/3 pi r cubed, so I have a constant there of 4/3 pi. I'm going to write that as 4 pi over 3. Now I have to take the derivative of r cubed. That's going to be 3r squared times dr dt. And let's go ahead and simplify that. That's going to be 4 pi r squared times dr dt. Okay, folks, just one last comment here on the sphere derivative we just took, rate of change of volume with respect to time. For those of you that can go into Wayback Machine and remember a lot of geometry from a couple years ago, I gave you a little fun fact about this one here. I said the rate of change of the area of a circle is proportional to its circumference. and the rate of change of the radius. Well, similar idea down here. 4 pi r squared is the formula for the surface area of a sphere. So we can see that the rate of change of the volume of a sphere is proportional to its surface area and the rate of change of the radius. So those are a couple little fun facts that hopefully you can impress your family and friends with. All right, this video is getting a little long. I'm going to chop it into 2 pieces. I'm going to end it right now and then pick up with example 1 in just a minute.